Okay, so in the last lecture we have derived a formula for the endpoint correlation function, which is the vacuum expectation value of time ordered product of n fields. And using the Wick's theorem, this can be expressed in terms of the normal ordered product of the fields and then all possible contractions times the normal ordered products. In today's lecture, we will derive the formula for cross section, decay width and so on, because these are the quantities that are these are the measurable quantities. So, you need to have a formula for the scattering cross section, when you consider two or more particles scatter with each other. If you have unstable particles, they can decay by themselves, and then you can determine the rate of the decay, decay width and so on. These are the two basic things that we will be working out. So, we will have a formula for the scattering cross section and as well as a formula for the decay rate for unstable particles. So, for scattering cross section, of course, you can have two particles coming and then interacting and then going out. For example, let us say you have E plus E minus scattering or whatever. The outgoing particle may be the same set of particles, or there may be different number of particles. For example, when you consider E plus E minus scattering, you may get E plus E minus mu plus mu minus or mu plus mu minus gamma, all kinds of things that you will be getting as outgoing particles. You need to find out the cross section for all these particles. So, let us, or you can have also more than two particles, let us say three particles interacting with each other and going out and so on. What we will be discussing in today's lecture is the case where two particles come. Let us say particle 1, which is incident on particle 2, which is at rest in the laboratory, and then there are a bunch of outgoing particles. We need to find the cross section for such a process. So, what I exactly mean by cross section? You consider, let us say you have a target here, which I will call as the particle 2, and then you have a beam of particle 1. So, this is the target, and this is the incident particle. Okay. Of particle 1 of type 1. It says false on this. What you need to know is what are the number of scattering events in this process. Naturally, there will be more events coming out. Let us say if this target is very dense. More number of scattering events will come out if the incident beam is also dense, very dense, right. So, the number of scattering event naturally depends on the density of the target, which I will call as rho 2. It also depends on the density of incident beam. If it is not dense at all, then the number of events, scattering events will be less, and so on. This will also depend, let us say, on the thickness of the target here. Okay. So, this I will call this as, let us say, L2, this length here. Similarly, it will also depend on this L1. What else it can depend? It can also depend on the cross sectional area here. If it is a if the beam incident beam comes only on a very small region here on this target, then the number of events will be less. If it comes on the entire thing, it will be more. Let us say both the incident beam as well as the target share a common cross sectional area, then the number of scattering events will also depend on the cross sectional area, which is common to both of these things. So, the number of events which I will call as n, it will be proportional to all these quantities, rho 1, L1, rho 2, L2, and A. The proportionality constant is what I will call as the cross section. So, the cross section for this scattering is determined by dividing this number of events by this quantity here. Similarly, when a particle decays, the decay rate is, the formula for the decay rate is even simpler. You consider some substance, some unstable particle here, and then there is a probability that one of these particles will decay. And this decay rate here will depend on the size of this system here, the total number of particles. So, the decay rate is basically defined by the number of particles decaying per unit time divided by total number of particles contained in that system. That is what is going to give you the decay rate. So, in these lectures we will be basically discussing scattering cross sections and decay widths, decay rates. We will derive formula for these quantities, and then we will see how can we apply these things. So, in our case we are considering interacting field, which is basically let us say you consider two type of particles. They were free as at t tends to minus infinity. Essentially they were free particles. At some finite time they come closer, they interact, they scatter, and then there will be outgoing particles. So, 1 plus 2 goes to a bunch of particles, 1 prime, 2 prime, n prime. This is the process that we are going to study, and what you want to do is you want to construct a wave packet, let us say for particle 1 as well as particle 2, or a wave packet for the two particle system, and let it evolve, interact, and then you go what is the probability amplitude for this system to go to some final state. So, essentially let us try to construct the wave packet for particle 1, which I will denote as 1. Normally if it is free particle, then you normally if the particle is an eigenstate of the momentum, then this is just, let us say, a k1 dagger acting on the vacuum. This is a one particle state with a definite momentum k1. Normally, what we would like to consider is wave packets which do not have a very well defined momentum, but there is a spread in the momentum, and so there is a momentum distribution which is peaked around certain value, let us say which is k1 bar. Okay. So, the particle 1 is a wave packet which is basically integrated over dq k divided by 2 pi q to k0 times some distribution which I will call as f1 of k, and then k here. So, this if this f1 is a delta function, if f1 k is delta k minus k bar, then you get the particle 1 to be an eigenstate of the momentum. It has a very well defined momentum. Otherwise, you can consider some momentum distribution here, and then you can construct a wave packet this way. This f1 is some distribution. You do not need to know the exact form of this f1, except that it has a fairly well defined momentum, which is the average momentum is peaked around certain value, which I will call as k1 bar. So, you have a distribution with a peak around k1 bar, and this is what is. The initial state is not a one particle state, it is a two particle state, right. We are considering a process where particle of type 1 and type 2 interact with each other and go to some final state. So, the initial state is basically dq k1 divided by 2 pi cube 2 k10 dq k2 divided by 2 pi cube 2 k20, and then f1 of k1 some distribution f2 k2 So, this state evolve, and both the particles interact at some finite time, and then what you would like to know is the probability amplitude for this state to evolve to some final state, which I will call as f, which has some momentum p1 or k1 prime, k2 prime up to kn prime. Normally, the outgoing particles can have fairly well defined momentum. You can detect these outgoing particles by some detector which have very good resolution, so that you can consider these outgoing particles in some momentum range dq k1 prime, dq k2 prime, and so on. We already know what is the probability amplitude for such a process. The probability amplitude will be given by, so if this is the final state, then the final state for the state I to be found in is given by right, where S is the S matrix for which we have derived the expression in one of these earlier lectures. Yeah.
Why have we assumed the final state to be momentum eigenstate?
We don't. So right now we are not assuming. Okay, we don't need to assume this the outgoing state to be a momentum eigenstate. So what we will do is when we calculate the cross section, we would like to find the differential cross section where the outgoing particles will have momentum which lies in some range dq k1 prime. So let us say the outgoing particle with momentum k1 prime, let us say 1 prime is the particle, its momentum lies in certain range dq k prime, because when you have the detector not only can measure what is the particle type, it can also measure the momentum of this particle in fairly accurately. So if we don't need the momentum of the outgoing particle, what we can do is we can consider the differential scattering cross section and we can integrate over all possible value of the momentum. That will give as what is the total cross section irrespective of what is the momentum of the outgoing particle. So at this moment we will not assume anything about the final state, we will just assume this initial state to be two different wave packets coming out close to each other and then interacting, and then there is some outgoing set of particles. That is all we are assuming. We will also not assume any particular form for these functions f1k and f2k, except that there is some momentum distribution which is peak, which has a peak around certain value. All right. So let us compute the probability of going some initial for the particle from some initial state to some final state WFI. That will be given by the mode square of this quantity we will be computing this quantity in a moment. You know this S matrix has an exponential form, and hence I can basically write this as the identity operator plus the rest of the term, which I will denote as I times t. Okay. And then the probability amplitude will basically be this one. What will the first term give? So this is this term basically says that there is a finite probability that, so you consider particle 1 incident on particle 2, on some target, there is a finite probability that these particles do not interact at all, they just go without interacting, and this is the term. Even if there is an interaction in the system, these particles can simply pass without interacting each other, and this term represents that. So, this is the forward scattering part. We will not be interested in such a term. So, we will just ignore the first term in this expression. We will be evaluating the second term, and then when the interaction takes place, what is the probability of this system of two particles, some which are in the state I, going to some final state. So, we will be evaluating the mode square of this quantity, which is a double f I. I will define this to be mode square of f I t. Okay. Let us substitute this expression for the incoming state in this formula, and then let us try to simplify the expression. So, let us see what we get when we substitute that. This quantity here, I will call this as again f I t I star times f, right. It is absolutely trivial. Now, I will put this formula there. So, what I will get is, for the first term, dq k1 divided by 2 pi cube 2 k1 0 d cube k2 over 2 pi cube 2 k2 0, and then f1 star of k1, f2 star of k2, then f I t k1 k2 star, and then I will have integration over dq k1 tilde over 2 pi cube 2 k1 tilde 0 dq k2 tilde over 2 pi cube 2 k2 tilde 0, then f1 of k1 tilde, f2 of k2 tilde, final state inner product with I t times k1 tilde k2 tilde. Okay. So, this is what we have to simplify, and then we have to express in a form. To do that, let us see this expression here. I can take a Fourier transform of this quantity. So, I will define as f I will define some quantity which I will call as f tilde 1 of x, which will be dq k times e to the power minus I k dot x f1 k. You define f1 tilde of x to be the Fourier transform of this f1 k, this distribution function. You can show that this complex scalar field in fact satisfies the Klein-Gordon equation there is this integration measure 2 pi q 2 k 0. This is first of all a complex scalar field. This field will satisfy the Klein-Gordon equation for the particle. What we will do is we will consider this term here. We will insert one identity. So, you consider one of these amplitudes here, okay. This, let us say this one f I t k1 tilde k2 tilde. If the outgoing particles have momenta k1 prime up to kn prime, they need to conserve the total momentum. The momentum of incident particle are k1. This state has well defined momentum. This is a 2 particle state with momenta k1 tilde and k2 tilde. So the momentum conservation tells you that this amplitude here must be proportional to the delta function. It will be 0 unless k1 tilde plus k2 tilde is equal to the sum of all these outgoing momenta of all these outgoing particles. So, this quantity here will be, for convenience I will put some factor of 2 pi to the power 4th here. It will have a delta function, delta of k1 tilde plus k2 tilde minus kf, where kf is the sum of momenta of all the outgoing particles. So, it will have such a term here, and then the remaining part of the amplitude I will denote this as f I this curly t k1 tilde k2 tilde. So, similarly you have the second term here. You can so let us consider this expression. With this WFI will become dq k1 over 2 pi cube 2k10 d cube k2 over 2 pi cube 2k20, then d cube k1 tilde and then there are these vectors 2 pi fourth delta of k1 plus k2 minus kf, right, and then 2 pi to the power fourth delta of k1 tilde plus k2 tilde minus kf. Then these two matrix elements which are f I t k1 k2 star times f I t k1 tilde k2 tilde, and then also I have f1 star k1 f2 star k2 f1 k1 tilde f2 k2 tilde. This is what I get. Now notice this, there are these two delta functions here. I can combine these two delta functions, then I can write this as delta of k1 plus k2 minus kf delta of k1 tilde plus k2 tilde minus kf is equal to delta of k1 plus k2 minus k1 tilde minus k2 tilde times delta of k1 tilde plus k2 tilde minus kf, right. So, we will use this form here. Therefore, instead of this I can simply write here this minus k1 tilde minus k2 tilde, and then the remaining part will go as it is. This is just delta of x minus a, f of x is basically delta of x minus a f of x. This is what is the formula that I have used here. Now I can consider this term, and I can write delta of k1 plus k2 minus k1 tilde minus k2 tilde as if you consider the 4-dimensional delta function, So, not only the energy, but the momenta are also not only the momenta, but also energy also needs to be conserved. So, you have to have 4 dimensional delta functions here instead of 3D delta, and I will use this formula for the delta function. There is a 2 pi to the power 4th. So, 2 pi to the power 4th times this is given by this. I will substitute it here, and when I substitute, what I will get is the following. dq k1 over 2 pi cube 2 k1 0, then dq k2 over 2 pi cube 2 k2 0, and then d cube k1 tilde over 2 pi cube 2 k1 tilde 0, d cube k2 tilde over 2 pi cube 2 k2 tilde 0, then d4x times e to the power minus I x dot k1 plus k2 minus k1 tilde minus k2 tilde, then 2 pi to the power 4th delta of k1 tilde plus k2 tilde minus kf, and then I have f1 star of k1, f2 star of k2, f1 of k1 tilde, f2 of k2 tilde, fi star tilde. Okay. So, it is a fairly straightforward job. Now, what I will do is that I will combine this k integrations, I will just carry out the k integrations by making the following assumption. What is the assumption? The assumption is that because we have assumed these functions f1, k, etc. are at some distribution which is peaked at some value k bar, let us say f1 k is peaked at k1 bar and so on. Therefore, the amplitudes here, I will assume that these amplitudes are basically equal to k1, k2, I will say that this is nearly equal to f I t k1 bar k2 bar, and also this is fairly close to I K1 tilde bar, K2 tilde bar. Then what I can do is that for this I will just substitute mod square of this. Okay. So therefore this so the assumption here is that these matrix elements are slowly varying, and then they are close to this, they are nearly equal to this quantity here. Therefore this probability density here is nearly equal to this mod square of this quantity, with this K1 and K2 are replaced by K1 bar and K2 bar. So I am not assuming this K dependence here. Then of course it is fairly simple, because what you get here is basically the Fourier transform of these 4 f's. So they are nothing but integration d4x, this one will give you f1 of x, this one of these thing, this factor will combine this to give you f2 star of x, and similarly here you will get f1 of x, f2 of x. Okay. So therefore the transition probability per unit volume per unit time, which I will denote as dWFi over dV dt, will be given by simply this expression without this integration over d4x. So what we have derived here is the transition probability per unit volume per unit time. We need to find the scattering cross section, which is basically this quantity divided by the incident flux when you have a single scattering center. So what you need to do is, you need to the differential scattering cross section is basically the transition probability per unit volume per unit time divided by the density of the number density of the target times the incident flux. So let us derive the formula for the incident flux and the number density for the target, and then plug it here. We will get the formula for the differential scattering cross section.